All right, ladies and gentlemen, in this video, we'll be looking at a special type of complex functions that are easy to work with, and it will involve what is called linear mappings. So we're going to be dealing with complex functions. Complex functions of this form. They look like this. F of z is equal to a times z plus b, right? Where a and b are complex numbers, right? So this will involve, so these functions will involve three types of transformations. So they will involve what is called a scaling. So multiplying by a number usually does that. Either shrinks or extends. Right? Depending on the modulus of that number, right? The second type is a rotation. This will involve taking the polar form of a complex number. Okay? Of a complex number. The last thing is a shifting. So if you add complex numbers of another one. So usually this quantity right here will deal with the shifting factor. Okay, so this quantity will deal with the shift, right? And the A quantity that's right here, oops, let me do another color. So this quantity right here, this deals with rotations, right? Rotations, or a, so they call this a dilation. So, or a dilation. Okay, or a dilation. But regardless, I'll show you how those work. Okay, so let me get rid of these. All right, so let's look at some examples. All right. So we want to find of S, which we'll call S prime. Vertices 1 plus I, 2 plus I, 2 plus 2i, and 2 plus 1 plus 2i. Okay. So this set will denote the set S in the z-plane. So here's my z-plane. It's X and then Y. And so we'll have 1, 2, and let's say 1 and then 2 here. So this will constitute a square. If I did this right. Okay. So this is S right here. Okay. And we want to look at what this function over here. So under the function, let's say t of z equals to z plus 2 minus I. Okay, so we have this function here, and we want to look at what this function does to our set S as indicated in the z-plane, right? So if I incorporate the transformation t over the w plane. Let's see what happens. Okay. So here is the w plane. All right, here's the w plane. And then we're just going to look at what happens to these points one by one, and we'll see what shape we'll get. So if I look at the first vertex, 1 plus I, this will equal to 1 plus I plus 2 minus I. So the i's cancel, and you will get 3. Okay, so 1 plus I will correspond to the point 3 plus 0I in the w plane. Okay, so w, u axis, and the v axis there. Okay, so that will correspond to 3, 0 in the w plane. If I look at the second vertex, 2 plus I, this would equal to 2 plus I, plus 2 minus I. So that will cancel the i's, and we will get 4, right? So the point 2I in the z plane will correspond to the point 4, 0 in the w plane. Okay. Let's see vertex number 3. At vertex number 3, 2 plus 2I, this will equal to 2 plus 2I plus 2 minus I. And that will equal to so that will equal to 4 plus I. 4 plus I. Okay, 4 plus I. So here is 1 here. And this point will correspond to, let me actually make this scale a little bit bigger so we can see it. So put 1 there. So this will correspond to the point 4 plus I. That's for the point 2 plus 2I. And then the last vertex, t is equal to 1 plus 2I. This will equal to 1 plus 2I plus 2 minus I. And that will equal to 3 plus I. So 3 plus I will be here. I'm actually write these out coordinate-wise. 4, 1, and then 3, 1 is here. So this will correspond to another square in the w plane. So that's S prime. Okay, so really it's just a shift. Okay, so you're shifting all the points by 2 plus I, by 2 plus 2 minus I units, excuse me, right? So that will correspond to a shift, right? Okay, so this is a shift, right? Next, let's look at what a rotation would look like. So a rotation will correspond to a function that looks like this. R of z is equal to a times z, where the modulus of a is 1. Okay, so basically what a rotation is, so we can write out z in terms of a polar coordinates, r to the e to the I theta. And so if we let a equal to e to the I phi, let's say, the radius is 1, so it's just e to the I phi, then a times z, that will equal to e to the I phi times r times e to the I theta. So this equals to r times e to the I times theta plus phi. Okay, so all essentially is this transformation would be is, okay, if this is my complex number z and it has a radius with a fixed radius and an angle theta, what this transformation will look like is just, well, the radius is kept the same, but this angle is added on. So this would be theta plus phi. Okay. If theta is positive, we're going counterclockwise. So that would be what that transformation will look like, right? So for an example, try to find the image of the disk. The unit disk under this transformation, f of z is equal to 3 times iz. Okay, spend a few minutes working on this example. If you come back, I'll show you the solution. Well done. I assume that you've worked on this example, and let's see what we'll get here and see if your solution is correct. So if I look at the z plane, right? So this set we're looking at is the unit circle and all the points that are in the interior, right? So this is the set S that we're talking about here, right? And so our function is f of z equals to 3 times iz. So let's okay, so the a value right here, the a is 3i, right? And so what we want to do is transform a into polar coordinates, right? So to write out this in polar coordinates, remember 3i will be a point that's on the positive y-axis, right? So 3i is a point in right here in the complex plane. So in polar form, right, a is equal to 3 times e to the I times pi over 2, right? Okay. The radius is 3, right? Right. This complex number, you can write this out as 0 plus 3i, right? The radius, the modulus of a, is just the square root of 0 squared plus 3 squared, which is 3 squared, so 3. Okay, so hopefully you got that. And that point is on the positive y-axis, so one of the quadrantal angles. So that would be at an angle of pi over 2 radians. Okay, so this is how you would look at this point. 3i in terms of polar coordinates. Okay, so if I let z be the polar form, re to the I theta is just any polar form, well then f of z, we can write this out as 3 times e to the I pi over 2 times r times e to the I theta, right? Okay, so really it's just 3 times r times e to the I times theta plus pi over 2. Okay. So S is the unit disk. So and all the points that are inside the unit disk. So the radius will always be less than 1. So so we can actually rewrite, well, f of z as 3 times e to the I times theta plus pi divided by 2. Okay, so essentially what we will have is this circle in the z plane, the unit circle, that will become a circle of radius 3 in the w plane. Okay. And all the angles are just they're added on by pi over 2, right? So if theta is 0, theta is pi over 2, and this is a radius 3 here. If theta is pi over 2, the new theta is pi, so we'll have, if I just extend this out over here a little bit more, this will be another point here, and we'll have another point here, and another point that's out here. So this would be another circle of radius 3. And we want all the points inside the circle. So its image would be the points W such that the modulus of W is less than or equal to 3. So it will be this set. So this example, this dealt with not only a rotation, but also a dilation. The circle grew bigger in size, right? By a radius of 3, in fact, right? So it grew by a factor of 3. So we dealt with a rotation and a dilation as well. So here's another one. I want you to work on this on your own as well. Find the image of the real axis. This is where y is 0. Under the function, let's say f of z equals to root 2 over 2 plus root 2 over 2i times z. Okay, here's another one. Try to work on this example. Okay, I assume you worked on this. Let's see what it looks like. I don't know if you notice the constant. This should look familiar, right? Root 2 over 2, this is how you would get cosine of pi over 4. And this value, root 2 over 2, is sine of pi over 4. So in your heads, this should ring some bells because this will constitute a line, essentially. So we want to look at what happens if we take the set S to be the line y equals 0 in the z plane. Okay. So here is my z plane. Okay. And so we want to look at the function f of z, and here is the w plane. W plane. And our axes are labeled as u and v. Now, if you notice, oh shoot, okay. Let me rewrite the function. Root 2 over 2i times z. So if I call this quantity a, so the length of a is actually 1. Okay, it's on the unit circle. And we know that theta is pi over 4. So we can rewrite a in terms of polar coordinates, e to the I times pi over 4. Okay, e to the I times pi over 4. Now, on the real axis, this is where the y value is 0. So essentially, z is equal to x, right? So there is no imaginary component. So we can rewrite this set as x times e to the I times pi over 4. Okay, so our radius is growing without bound, and we're fixing our angle at pi over 4. So therefore, we'll produce the line y equals x, or I should say u equals v on the w plane. All right. So this will constitute the line u equals v at pi over 4. Okay. So actually it's yeah, so yeah, so and it's negative, so yeah, so it'll constitute a line. Okay, so hopefully that made sense. So this is S prime. Okay, so let's see. So to recap, so here's an overview of a linear map in the complex plane. AZ plus B, where A is not 0. I mean 0 plus 0I. Okay. So for W naught equals to F of Z naught for some Z naught in the complex plane, to figure out a rotation, you can rotate Z naught about the angle of the argument of A about the origin. That's how you deal with rotations. 2 magnifying points. In other words, shrinking or stretching points. You can magnify the result by the modulus of A. C, to deal with translations. So shifting by a factor of B. Okay. And what's great about linear maps is they always preserve angles. That's going to be very important. We'll deal with what are called, in this course, I think, conformal mappings. And these are mappings which you can change the way they increase or decrease in size, but they always, but their angles will always be the same. That's what a conformal mapping is. And we'll look at those in great detail eventually. So let's do one last example, and I'll write out some problems for you to work with. So find a linear mapping from S to S prime, where S is the triangle with vertices 0, 1, and 1 plus I, not 1 plus 1, 1 plus I, and if we're given S prime is the triangle with vertices 2i, 3i, and -1 plus 3i. So work on this example, and let's see what type of function you'll get. Okay, so pause the video and try to work on this on your own. Okay, congrats on reaching this point. So I hope you worked on this example because I'm going to go over it right now. So in the z plane, we want to label out these vertices of the right triangle. It's going to be a right triangle. So we have one vertex at the origin, 0 plus 0i. We have one at 1 plus 0i. So x, y is the other arrow. So the origin, the point 1, 0, and the point 1 plus I. So 1, 1. Okay, so this is our right triangle here. Okay, and what we want to do is if we're given S prime, right? If we're given S prime, which looks like another right triangle, so here, so we'll have -1, we'll have a 2 and a 3 up here. So -1 plus 3i plus 3i. Let me do another color. 3i and then 2 i's here. So this is S prime, and we have S over here, right? So we want to come up with a transformation. Okay, so what this looks like is, okay, this triangle looks like a rotation, right? So this, I'm sorry, this triangle on the right, on the W plane, U and V is there. So this triangle on the UV plane looks like a rotation of the triangle in the Z plane. Okay. And it looks like if you rotate it 90 degrees, so if we have this triangle, if you rotate it 90 degrees, right, it will be just this triangle, right? Well, something like that. Okay, so essentially, if we rotate 90 degrees, right, we can get a triangle that looks like this, right? Okay, so yeah, so 1 plus I, if I rotate 90 degrees, I multiply by I, I'll get -1 plus I, which is in the second quadrant. Okay, and I'll have 0i. Okay, all right, and then all we have to do is, so this would be at the point -1, 1. So this will be at the point 0, 1, and this is still at the origin. And then all we have to do is just shift up this triangle by 2i, right? So this is iz plus the shifting factor is 2i, right? Iz plus 2i. And this right here would be the proper function to shift this triangle in the Z plane into this triangle in the W plane. So I hope that made sense. Okay. So here's some problems for you to work with. Problems. So, and I forgot to write out the page number. So, let's see. That is 69. So 5, 8, 10, 14, 16, 18, 20. Okay, so that is the lesson for linear maps of complex functions, right? So in the next video, I'll look at different power functions in complex numbers. So stay tuned for that.